Hello everyone and welcome back to my channel Gyan Sampada. In our previous class we were dealing with Weiss molecular field theory and today's class will be based on that itself. If you have not gone through the previous class where we considered the Weiss molecular field theory, we understood some of the details of the Weiss molecular field theory based on the equation given by Weiss. Then first go through it, because based on those equations itself we are going to learn some concepts in our today's class. So let's start our today's class where we are going to understand the relation between the Weiss constant, which is taken as lambda, and the Curie temperature, which is the transition temperature Tc. According to the quantum theory of paramagnetism, we saw that magnetization M is equals to Ng mu b tan hyperbolic of x, where x is a function of temperature. And according to Weiss theory of ferromagnetism, we saw that M is again a function of x, but the nature is straight line. That is, M is equals to kT divided by mu naught mu p g into lambda into x. So according to quantum theory of paramagnetism, we are having a hyperbolic curve, but according to Weiss molecular field theory, we are having a straight line when we plot magnetization as a function of x. So based on the same equation, we have drawn some conclusions in our previous class. So making use of these two equations, let us get the relation between lambda and Tc. So here in the LHS part, both are same, that is magnetization. So both can be equated, which is nothing but Ng mu b tan hyperbolic of x is equals to kT x divided by mu naught mu b g lambda. If you consider at Tc, that is temperature at Curie temperature, because we need the relation between lambda and Tc. Here we are already having lambda. So now let us consider temperature equal to transition temperature, and we have seen that when temperature is equals to transition temperature, spontaneous magnetization is going to just vanish. That is, the curve will be tangential to the hyperbolic curve at the origin, and tan hyperbolic of x is going to be almost equal to x itself, because x is very much less than 1. So instead of tan hyperbolic x, we are writing x for t is equals to Tc. So if you just cross multiply, we can say that lambda is equals to kTc as it is divided by mu naught n into mu b into g whole square, because x and x are going to get cancelled. And this is the relation which is going to give us the relationship or dependence between the Weiss constant lambda, which is going to determine the strength of interaction between the magnetic dipole moments in the ferromagnetic material, and Tc, which is the transition temperature where the spontaneous magnetization just vanishes. And also that while solving the Curie-Weiss law, we got the equation C lambda is equals to Tc. Using the same equation, we are having the lambda value. If you substitute, then we can observe that C is equals to mu naught n into mu b g whole square divided by k. That is, taking Tc divided by lambda and taking all the other terms on the LHS side. So finally, we are getting an equation for Curie constant, and clearly we can observe it is having different terms which are again constants. So for different materials, this Curie constant is going to remain same. So if we know the value of transition temperature, easily we can find out the Weiss constant lambda, and generally we say that transition temperature of ferromagnets is almost equal to 1000 Kelvin. That is, for iron it is 1043 Kelvin, whereas for cobalt it is 1393 Kelvin, etc. So by substituting the value of Tc, lambda can be determined. And if we take the ratio of Tc by lambda, we get the Curie constant. So let us substitute the value of Tc almost equal to 1000 Kelvin, and n is equals to 10 raised to 29 per meter cube. Then we observe that the Weiss constant is of the order 10 raised to 4, which is according to Weiss molecular field theory. So based on this and our previous class, let us know what are the merits and demerits of Weiss molecular field theory. First, the successes of Weiss molecular field theory is that he wanted to explain the different phenomena which are taking place in ferromagnetic material, and he has successfully explained a wide range of ferromagnetic phenomena like the spontaneous magnetization, the temperature dependence of it, and also the behavior of the material above transition temperature. That is, above transition temperature the state is disordered, that is, randomness is observed in the arrangement of spins, which is nothing but non-ferromagnetic state or paramagnetic state, and above transition temperature Curie-Weiss law is satisfied. It is experimentally also proved. So these are the merits of Weiss molecular field theory. Coming to the demerits or the limitations of Weiss molecular field theory. Mainly there are two limitations. The first and the most important is the nature of the field and its origin is not explained by this theory. The assumption is done, that is, there exists a molecular field which is due to the interaction between molecules and the magnetic moments. But how it is going to originate and what type of nature it is, whether it is due to electron-electron interaction, whether it is dipole interaction, it is not explained. So it was supposed to be originated due to the nearest neighbor dipole-dipole interaction. And if it was so, then such interaction would give rise to a field which will be having the order mu b by a cube, where a is the interatomic distance in ferromagnetic crystal and mu b is the Bohr magneton. And if we take in general the ratio of these, the field will be approximately equal to 10 raised to 3 Gauss. But according to Weiss molecular field theory, if the transition temperature is almost 1000 Kelvin, then exchange field, which is given as lambda into m, the maximum spontaneous magnetization occurs at 0 Kelvin. So ms of 0, lambda we saw that it is of the order 10 raised to 4, and multiplying by ms of 0, that is maximum magnetization, if we consider it equal to 1000 based on the n, j, mu b value, then the exchange field is of the order 10 raised to 7 Gauss. So the difference between 10 raised to 3 and 10 raised to 7 Gauss is huge. So this discrepancy shows that the simple model which is based on dipole-dipole interaction cannot be reason for ferromagnetism, which was used as an assumption in case of Weiss molecular field theory. So for this, some much stronger type of interaction is required, but what actually it is not explained. That is main thing. According to the theory, the field which is HW, that is Weiss field lambda into m, is large, but what is the reason for the large amount and the origin of the exchange field is not explained, which is the main limitation of Weiss molecular field theory. Coming to the second limitation is that this theory fails to explain the behavior of ferromagnetic material in the vicinity of transition temperature. That is, what happens just near to the Curie temperature is not explained, that is at and just in the neighborhood of it. He says that as temperature tends to transition temperature, susceptibility tends to infinity, which is not possible. So what happens actually in the neighborhood of transition temperature is not explained, which is another important limitation of Weiss molecular field theory. And also it is said that the Weiss constant is independent of temperature, but experimentally it is found that it slightly differs with respect to temperature, which can be again a limitation for Weiss molecular field theory. But mainly these two reasons are very important. So this is the total concept of Weiss molecular field theory, where in our previous class we understood about the assumption, the equations, the details about Weiss molecular field theory, and today we understood using the Weiss molecular field theory what is the relation between Weiss constant and Curie temperature, by which we can even calculate the Curie constant, and also what actually are the successes and limitations of Weiss molecular field theory. In order to overcome these limitations, there has to be some upgraded theory. So in our next class we will be dealing with Heisenberg exchange interaction. And this is for today's class. Study well. Thank you.